Alright, in this video we'll be looking at the expected value of a random variable. So let's bring back our die and the random variable x associated with rolling this die. We saw that we could reach into this magic box and grab a number from it, and each time we did that, it would have to quickly roll a die and tell you what it got. So all these different numbers could appear, and we could keep going for as long as we like, but we could ask the question of what the sort of long-term average would be. Why I say long-term is because we're not asking for the average of these numbers or any particular set of outcomes. We're not actually going to do the experiment, right? There's no sense in which we can add up some scores and divide by how many there are, because I'm not looking at any particular set of scores. Right? The whole idea of a random variable is not to look at particular outcomes or sets of outcomes, but the general process. So to ask for an average is slightly different in both calculation and interpretation, and that's why we're going to give it a special name. It's going to be called the expected value. Okay, we'll actually explain this first by looking at an even simpler experiment, flipping a coin. Okay, but let's make it a little more interesting than that. Let's say we're playing a game where if it lands on heads, you win $10, but if it lands on tails, you win $20. Right? How much would you expect to win per game? So each time the coin is flipped, how much would you expect to win? Okay, I like to think of it this way. This rectangle here represents the two possibilities with the coin flip, heads or tails, and we'll put the actual outcomes of this game inside. So for heads, it's $10. For tails, it's $20. Now, assuming it's a fair coin, each of these outcomes would happen with probability 1/2. So how much would we expect to win each time the coin is tossed? Well, half the time, it'd land on heads and we'd win $10. On average then, this amounts to half of 10, which would be $5 per flip. Likewise, half the time, it'd land on tails and we'd win $20 instead. And on average then, this amounts to half of 20, which would be $10 per flip. In total then, the average coin toss would earn you $15. And there are two things I want you to notice here. First, when we say we expect to win $15 per game, that's kind of strange, because it's impossible to win $15 in one game. You either win 10 or 20. There's no option for winning 15. So we're not really ever literally expecting to win $15 in any single game. It's not a literal real-life expectation, but more a mathematical one, and more precisely, a long-term mathematical expectation. Okay, the interpretation is more this way. It's as if, say, you play 1,000 games, then you can expect to earn close to $15,000. The more you play, the more accurate this expectation would get. So if you played 1 billion games, you'd really expect to be very, very close to earning $15 billion, so $15 per game. Okay, and this idea has a super technical name in the world of statistics. It's called the law of large numbers. Right, where the more times you try the experiment, the more times you do it, the closer on average you get to the expected value happening each and every time in total. Okay, alright, so that's the first thing to notice. It's not a literal expectation, but a mathematical one, right? A long-term mathematical one, sort of giving you a general average kind of idea over the long term. The second thing is, you're probably thinking, why do so much acrobatics with the probabilities and multiplying and adding? Well, you've probably noticed that 15 is just the normal average. It's halfway between 10 and 20. So why can't we just stick with that? Well, the reason is that the normal average calculation is only that simple when the outcomes are equally likely. Alright, so let's change things up a bit and switch to a loaded coin to illustrate. Alright, load it so that it lands on heads 3/4 of the time, and on tails only 1/4 of the time. Then we can see how the way we thought about it before makes things just as easy. We land on heads and earn $10, well, 3/4 of the time. So on average, this amounts to 3/4 of 10, which is $7.50 per flip. Similarly, we land on tails and earn $20 1/4 of the time. So on average, this amounts to 1/4 of 20, which is $5 per flip. In total then, the average coin toss would earn you $12.50. Slightly less than the previous answer, of course, because we're now much more likely to land on the outcome with less money. It's also interesting to note here that the heads outcome actually contributes more to this expected value than the tails outcome. Alright, what this means is, say if you played like 1,000 or 1,000,000 games and you put all the money you got from the heads flips into a pile and all the money you got from the tails flips into another pile, then even though each individual tails earns you twice as much money as an individual heads, because heads happens so many more times, you'd most likely find that the heads pile has a greater total than the tails pile of money. Okay, so let's generalize this working. We'll keep the calculation we did and put it up the top here and try and write down the pattern. Right, so what were those green numbers again? Well, each green number is a particular outcome. Right, in general, it would be some possible result we get when asking a random variable magic box guy for a number. And each pink number is the probability of getting that particular outcome. Okay, so each outcome gets multiplied by its own probability. Then the expected value comes from calculating this product for every single possible outcome, then adding those answers together, which is exactly what we did with the coin. Okay. And we really could stop here, but here's how we write it in fancy maths notation. So for the expected value of some random variable, which we'll label with a big blue X again, we write this as E of X, so E bracket X, like that. Just as how P of something stands for probability of, E of something stands for the expected value of. Then the formula starts with a symbol that represents this idea of adding up a whole bunch of numbers. Now, that idea of adding things up is represented by this Greek capital S called sigma. All right, and so what are we adding up? Well, all the guys inside that orange box there. So each outcome, which we've traditionally used the little green X for, multiplied by the probability of getting that outcome. So here we meet this expression again to say the probability that our random variable, big X, hands us that particular value, little x. Okay, that might look a bit scary, so let's go over each piece of this formula again. Alright, E of X just means the expected value of the random variable X, a long-term average of what you'd expect to get from X each time if you kept on asking that magic box for numbers over and over again. On average, what's the value of each one? This crazy sigma symbol just stands for a sum, adding things up. And it's implied that you're adding up or you're summing over all possible outcomes, so across the entire sample space and every single value that little x could be. Right, then what are you summing up? Well, it's each outcome, little x, multiplied by the probability of getting that outcome from your magic box, the random variable, big X. Okay, so that's the formula. But look, in many practical contexts, especially if you're just starting out, just getting the feel of calculating these things, it's often easier to just have this idea in your head, right? So just think of each outcome multiplying by the probability of getting that outcome and then adding them all up afterwards. Okay, the formula is useful to have, but really mostly when we do more complex manipulations with it and algebraic stuff further down the track. So let's just see one example of the calculation from your book to finish. Okay, it says a game uses a spinner with numbers 1 to 12 equally spread around it, and you win $3 for spinning a number bigger than 10, $2 for something less than 4, and you actually lose $1 for any other number. That's bad. And it's asking for how much money you're expecting to win or lose per game, right? So notice there's actually possibilities for losing money now, and of course we use negative numbers to represent that. So here's what the spinner would look like. The $3 case is for numbers greater than 10, so that's either 11 or 12, and I'll label this section with a positive 3, since we're winning $3 here. The $2 case is for numbers less than 4, so that's either 1 or 2 or 3, and again I'll label this section with a positive 2, since we're winning $2 here. we lose $1 for every other number, so that's those ones there. And this time, I'll label the section with a -1, since we're losing money here, and that's one of the key takeaways from this example. We'll use positives and negatives to represent things like earning money and losing money, or some sort of directed situation like that, okay? Alright, so now we just go through each of these outcomes one by one. Alright, we could earn positive $3, but this only happens in 2 out of the 12 possibilities. So we multiply that by 2 out of 12. Okay, so we're multiplying the outcome by the probability of hitting that outcome. Or we could earn positive $2, but this happens in only 3 out of the 12 equally likely possibilities, so we multiply by its probability 3 out of 12. And finally, we could lose $1, so effectively that's getting -$1, and this happens in 7 out of 12 equally likely possibilities, and so again its probability is 7 out of 12, and we multiply that -1 by 7 out of 12. Okay, so finally we add up all these possibilities and we end up with 0.42, which means on average we expect to win 42 cents per game, right? Win because it's positive. And again, this is a long-term average. It's impossible to actually win 42 cents in a game, right? But it's more saying, for example, if we played 1,000 games, right, we'd be likely to earn around $420, right? And so that's what the expected value of a random variable is and does, and how to calculate it, right? Next time, we'll discuss some properties and a special case of this, so I'll see you then. Thanks for watching.